We'll actually describe now another method of doing verification on CAN-based systems. The overview is shown here. Firstly, I will describe the challenges that are present in today's CAN-based systems. Then I will proceed with more model-based architecture describing the method that is used, and I will conclude with application of the results and experimental studies that were done, and the ongoing work. So first of all, I just show here an automotive application. This is just an example. And as we can see here, we have several control units, and they are connected through the CAN bus. And there is a dashboard, such that, as for example here, we have the lights control, and the lights can contain many subsystems, such as the front lights, the rear lights. So this grows the complexity in some such systems. So the system design, of course, becomes difficult. So what do we do in order to solve this kind of problem? We organize and abstract the communication complexity of CAN, such that we can use higher layer protocols in order to expand also its usage to a wide range of applications, including medical devices, maritime electronics, and photovoltaic systems. So, but in the end, what happens is that the system integration and validation is difficult because, as we can see here, we have several communication layers, and these communication layers actually remain a challenge for us in order to design the system successfully and to develop it from scratch, to be correct by construction. So what we do in order to verify this system, we use conformance testing. And conformance testing will verify that the system is correct, that the system will work in the end, and it will also contain interoperability of the devices. But what happens with component testing is that it occurs only late in the development cycle, and also it requires the final system implementation. This means that actually, if something is wrong, this can lead to a from-scratch development of the system, and also we cannot analyze performance in this kind of situation. So what we move forward to is the model-based design. What the model-based design allows us to do is that we can describe the behavior and functionality of such systems, and actually to separate the concerns between hardware and software, provide the usability of artifacts and modularity. So the previous work in this domain was based on multi-language frameworks in order to provide automotive system design flow, which means actually that all these formalisms were unrelated. So it lacked of continuity, which is important in the design flow. And what we propose is that we have a design flow for CAN-based systems, which is rigorous, which is based on one single semantic framework, encapsulates the protocol communication mechanisms, and then we can also incrementally build the system using composite components from simpler components. And such a design flow, as for instance here, as shown here, we can have the application software as input, and we can have the communication mechanisms of CAN as long as the hardware, and we can take all this in account in order to build a system model according to a translation from the application software to application model. And in the other end, we can see that we can have a protocol model which actually uses a library of components, and these are done by tools, such that if the concerns are separated upon the software and the hardware, we can use this transformation tool in order to build a system model. And then you'll say what is the reason that this system model is built. So the reason that the system model is built actually is not only to verify the system with properties and do performance analysis, simulation, and all the things that are important in such systems, but also to generate code which actually can be deployable in the platform, such that I can say that I will have a system which is running on a bus, and then I will deploy the code to each device, and I will successfully instantiate it, and it will work. From a description which is given actually in the application software, and the description which was given for the hardware, which means actually that I have a correct by construction implementation. So I will proceed now with a more detail about the framework that is used. Mainly the framework was used is BIP, and also there are associated tools with the framework. But BIP is a structured three-layered framework, and as you can see here, there are atomic components which actually model the behavior of the system, and there is glue upon them on the other layers in order to provide actually the composition of the whole system. So, for instance, here we can see the first layer, and we can see two atomic components. The one on the left and the one on the right. These are finite state automata, and to describe more, we can also send data, we can also have functions upon this automata, and they are described in C and C++. So there is a built-in language, but these are the data transferred through functions in C. So here we can see that the behavior of the system is more analyzed by states, which is shown here, and transitions from the states, which actually model the behavior of the system in a more abstract way, such that they can have transitions, and upon these transitions, they are labeled by ports. And these ports are used as interfaces in order to communicate from one component to another. So how the communication is done? This is done through connectors. How I connect components which are actually generic, and I can reuse them to each other, such that when a transfer of data is done upon this connection here, this interaction here between these two components, accordingly a transition will be followed, so that the component will go to another state. So what happens, as in this case, that two states are two transitions are enabled in that state here. So we have another layer which actually is solving effectively the competing interactions, such that in this case this interaction will be executed, and the other one will be probably executed at another point. But when they are both enabled, this is the important thing. Only this will be executed. So the toolset of BIP provides many source transformations. We also have code generations by dedicated compilers, and we also can translate from various languages, and we have according tools to BIP. If you want to have more information about the framework, you can visit this website. And now I will proceed with a model of the CAN protocol. So how this library that I explained before is structured, and how we take in account all the functionalities of CAN. So I just supply some specifications here, as for instance that this particular model is for the classical CAN, and it's modeling the high speed and the basic CAN controllers and interface. And it doesn't have an error model, such that it cannot consider transmission errors. So if I have, for instance, a subsystem of the previous system, and you can see here different devices connected to the bus, this is modeled as a library. So what this library contains is the components. So the hardware components which are actually interacting with the bus. So move in more detail about what is really happening in that situation is that you can have different CAN stations which can receive requests from the application layer and accordingly communicate and interact with the bus in order to send each frame field, and upon the reception of the CAN bus will broadcast to all the CAN stations, and this is a two-step process, and then when the frame is received, it will interact with the application layer in order to process it. So in more detail, this particular domain that I analyzed is based on data transmission and data request, such that we can have identifiers, length, payload, whatever we want inside the transmission data inside the frame. So the CAN station component, as I illustrated before, is a compound component, which means that it's actually it has two behaviors and two atomic components, which I illustrated before. The one on the left is the controller, which actually receives the requests from the application layer, and then accordingly stores them inside the queue, which can be FIFO or HPF. And then when it receives a frame, it will interact with the filter, whereas the filter in the other side, we can say that it's implementing the acceptance filtering mechanism, and it will accept the frame accordingly, or it will reject it. So when it's accepting, it will send also to the application layer. So this is just an example. I illustrated before the behavior of the atomic components, and here is the one particular component, the CAN bus. What is highly important here is that you can see the sequential transmission of each frame field upon the transitions that follow the interactions. And is also having a timing model, which is most important because it is a discrete time advance, which means actually when I send one bit, it will take a particular time of one tick. Tick is also is a time unit, and here is actually denoted by the port tick, where you can see that each transmission of each field, it will take a fixed number of ticks. So in this case here, you can also see that bit stuffing is taken in account, but I will not go into further details about this. So the application model is, on the other hand, it's also important in order to construct the system model as I described before. How does the tool work? It consists of a number of devices. The devices are generating a set of frames, and these frames can be periodic, event triggered, or purely stochastic, which means actually that they can be also generated with or without offsets, and they can be abortable or not abortable. So currently it's provided by XML-based descriptions, and I will also illustrate some examples with a focus on the transmission part. So as we can see on the left, we can particularly model an ECU with periodic transmission, which means that actually upon the expiration of the period, the frames will be generated and sent as a frame request over the bus. Whereas on the other hand, we can see here a more stochastic ECU, which actually implements a transmission jitter, which is added to the period and therefore generated. Actually, it's added here on this particular domain, and it's based on a particular distribution that is given as an input. So finally, I come to the point that, okay, I mean, maybe you were not interested about this, but I come to the point that how do I use these separated models in order to use the transformation tool and construct the system model. So as I explained before, I have a set of devices on the application model. I have actually the library of the CAN, which is the protocol model, And this application of glue, as I explained before, which is here modeled by interactions, will allow me to have a set of devices which will generate frames and will be connected to one or many CAN stations accordingly here in this scheme. So I move now to the application of this context, and first I will describe how a deterministic powertrain network was modeled using the BIP design flow. Here we see that we have 5 devices. They have periodic frame transmission with a according set of identifiers, period and payload. We have a fixed number on the bit stuffing, and we also model a bus which has a bit rate of 500 kilobits per second. So what is also important here, as I illustrate, is that the load was equally distributed upon the devices. So just some information on the experimental results of the system model, and what is particularly of interest is actually how we can use this in order to, now I focused on the simulation, but I can also describe later, I will also describe later about the other capabilities. So as we can see here, we have the frame identifiers in increasing order, and we can see a 3-step analysis, minimum, average, or maximum response times, and which is pretty regular according to the priorities of each methods. So 1 hour of serial system time here was simulated in 5 minutes and 30 seconds. And if you also want to of course, compare or contrast the results, the same results can be obtained using the real-time at work simulator, a real-time Gamba simulator, which has a much shorter simulation time. Whereas in this context, I can also do some stochastic analysis, which means that actually I'm not only constrained on a deterministic domain, I will also provide some jitter for every period, and I will also provide stochastic bit stuffing according to distributions. And then I can see that I have a more normalized, a more stochastic behavior in each, for each frame. So this actually is a 3-step analysis, doesn't allow me to perform and conduct construct the distribution of a particular message. So if I focus to a particular message, one of these messages, I will see that it will have a probabilistic distribution which actually can be used for analysis, and I will use also for verification of the system. So, so this particular analysis, okay, I described before that Artosim is a powerful simulator. It has a lot of analysis, but this analysis cannot be performed using it. So, so to conclude, I presented today a design flow which was rigorous, which was correct by construction, and also it allowed me to separate the software and hardware design issues. It was fully automated, supported by tools. They are open to open source. Whenever you want, you can really access them. And you can also perform performance analysis. You can also verify properties upon deadlines on a particular frame, and you can also generate code, C or C++ code. And the ongoing work is particularly based on the selection of the appropriate distribution for the bit stuffing. We also have on BIP a translation from MATLAB Simulink models to handle more application software to BIP, and we also have several tools such as the statistical model checking, where we can verify properties. We can generate optimal device configurations now, and there is a particular work that I'm working on at this point of time. It's based on CAN higher layer protocols such as CANopen, which is the most popular one. So thank you for your attention. If you want to have more information or related to ConFD, you can look on the paper or you can send me an email.